So we've got a table of some redox half cells, and you can see the question is asking us to make a cell from system number 2 and system number 4. So that's the Fe3 plus Fe2 plus system and the silver system. So a couple of rules to discuss to get you going in this construction. So rule number 1 is the most negative half cell is on the left. Rule number 2, providing you've done rule number 1 correctly, the left half cell always represents oxidation. If you look at the two numbers we have, we've got 0.34 volts versus 0.77. So clearly, redox system 4 is the more negative of those two. So let's begin the construction of the cell. The half cell on the left must represent an oxidation. Now, if you look at the data table, and this will be true of data tables in textbooks or perhaps the notes you've been given in class, the half cells are always written as reductions, but that's just convention. You can't have two things being reduced. In a redox reaction, one thing is oxidized and the other thing is reduced. So that means we have to change this equation, the one I've just circled, to represent an oxidation. So oil rig, oxidation is loss of electrons and reduction is gain. The silver half cell has to be written this way in the direction of my blue arrow because that represents an electron being kicked out, being lost from the silver. Let's set this up. We have the left-hand side is the silver electrode, which will be Ag. I like to write the half equation underneath to remind me of what's taking place. And then you'll see that the electrode is going to be made of silver. And then the electrolyte, which is the liquid around it, is going to contain the Ag plus ions. So the electrons are being generated in this half cell, the left one, because it represents an oxidation. So the electrons will flow up the wire along to the other half cell, pass through a voltmeter, and then into this half cell on the right. Now the one on the right, let's zoom in, is this one, and that stays as it is. So Fe3 plus is going to be reduced to Fe2 plus. But what you will notice is this half cell contains liquid species. Now we need an electrode, and obviously you can't have a liquid electrode, so we need something solid that's conductive. So the obvious choice is a metal. And the metal that is used as a conductor when we're investigating liquid half cells or even gas half cells is platinum. So the reason why platinum is used is threefold. Number 1, it's an excellent conductor of electricity. Number 2, it's chemically inert. So if you think back to the reactivity series, it's basically right at the bottom of the reactivity series. It's not going to interfere then with the cell reaction taking place. And number 3, particularly with gas half cells, it's really good at adsorbing gases, which means gases stick very well to it. So it's just excellent for this purpose. So the platinum then is going to be submersed in the electrolyte, and in that electrolyte we're going to have the two ions, Fe2 plus and Fe3 plus. So what would happen, right, is the Fe3 plus would go up to the electrode, like so, like I've just done there with that small arrow. Then it would collect the electron and Fe2 plus would be produced in its place. Right, finally is to connect the two half cells with a salt bridge, which is this green line here. What a salt bridge does is it just allows the passage of ions between the two half cells and is made from a group 1 salt, usually say sodium chloride, potassium nitrate. Any one of those is good for this purpose because group 1 salts are very soluble in water. So it completes the circuit and allows the passage of charge between the two half cells without them having to mix. So the electrons are made here and they flow from left to right in the direction of these red arrows. So as the electrons are being made on the left hand side, this is therefore the negative terminal, which means the other side is going to be the positive terminal of the cell. Finally then, we need to put in some conditions. So the conditions for these standard electrochemical cells are always the same. A temperature of 298 K, a pressure of 1 atm, so 1 atmosphere pressure is about 101,000 pascals. And then finally, concentrations. Any concentrations of solutions must be 1 mole per decimeter cubed. So the concentration of the iron solutions or silver are all going to be in 1 mole per decimeter cubed. So draw a label diagram to show how the cell can be set up in laboratory. That would be the answer. And typically this sort of question is about 6 marks and is part of a bigger question where they go on to ask about, well, what voltage does this cell produce? What is the overall redox equation? What is the cell statement? Now, if you're thinking about that information, well, I've covered that in the videos I've attached in the description below. So please go and watch them next.